All right, any questions? Luis, I believe you said yes?
Yeah, master set, question 5 to 9.
This is master set 8 through 10.
Yes,
Question 5, you said?
5 to 9.
5 through 9, okay. So 5, you've got a 10 kilogram mass is formed into a ring with a radius of 5 meters. It's spinning around its normal central axis. And when I say normal there, I'm talking perpendicular. So we have a ring. All right. We have a ring here, and it's spinning about some central axis. So the ring is spinning around like that. I give you mass. I give you mass and radius and angular speed. So I give you mass, radius, and angular speed. And then it magically becomes a disk, so it goes from being a ring to a disk. And what would the new angular speed be? So mass and radius stay the same, well, it's a closed system. Okay. In a closed system, there are two things that will definitely be conserved. What are they?
Energy.
3 if you want to throw that into it. Energy is not necessarily going to be conserved, well, sure, we'll throw energy into it. It depends on the energy bit. Depends on what you're looking at. But what is conserved in a closed system? Besides energy.
Angular momentum.
That's one of them, and the other one?
Inertia.
Acceleration? No, sorry.
No.
No.
We are assuming that mass is not changing in this course. However, mass can be converted into energy, which is part of the hedging of energy. Sure, depends on how you want to look at it.
Is this moment of inertia?
Not moment of inertia. But you have the right first two syllables. That's it. Yeah, angular momentum, as you said, and then just plain old linear momentum, or momentum as we generally call it. Now this one's an angular momentum problem. And we're just saying that the initial angular momentum is equal to the final angular momentum. Because it is a closed system, angular momentum is conserved. So then it comes down to, what's the formula? Well, let's think about regular momentum. What's the formula for regular momentum?
Mass times velocity?
And so this is the angular or rotational analog of that. What's the analog of mass when you get into the rotational system? Say it again?
Is it inertia?
Close, I need more than that.
Rotational?
Oh, either one, rotational inertia or moment of inertia. Inertia by itself is more of a, kind of related more to mass itself. So it's moment of inertia. And what's the angular analog of velocity? I think you're making the symbol, Brianna.
Omega?
Yes, and which is a symbol for, somebody help her out.
Angular velocity?
Yes, angular velocity. And so angular momentum is just the moment of inertia times the angular velocity. And because it's a closed system, whatever I times omega is initially, that's equal to I times omega finally. we're trying to find this. We're trying to find that. I give you this, I give you enough information to find this and this. So it becomes a plug and chug once you recognize what the formula for moment of inertia is of a ring. And what is the formula for the moment of inertia of a ring?
Mass times radius squared.
Yep, just mr squared. I of a ring, rotating about its central axis. Yeah, the more traditional convention, r squared. This is about normal central axis. And then the moment of inertia about a disk, about normal central axis. What's the formula for a disk?
When did we do something?
It is not.
Half.
Because the ring is nothing in the middle, we have to take that into account. Sorry, I cut.
Oh, half MR squared?
Yeah. So, I give you the mass and the radius, you plug in, you find I initial. It's the same mass and radius the second time, so you just plug in, find I final, and then it's a matter of solving. Is that sufficient, Luis, or did you want?
Yeah.
Okay.
Cause I was comparing my notes that I have to that. I'm kind of understanding it
Okay, good. Other questions at the moment? Well, we'll start out. Any other questions on this one? Other questions? Isabella? Oh, that's right, you had others, Luis, so we'll get back to the other ones in a moment. Isabella?
4D.
Which one?
4D.
4D, D as in dog.
Yeah.
So we got a car going around a curve with a radius of curvature of 110 meters. So if it's not banked going 30 meters per second without sliding, what is the centripetal force acting on the car? Oh, that's C. D, if 30 meters per second is the maximum speed without slipping, what's the coefficient of static friction? Okay. So from an overhead point of view, we have a car going around a curve. Let's assume it's traveling in that direction, that's the direction of the velocity. In other words, that's the direction the car wants to go, but it's not going to, it's gonna make the curve without slipping. So what are the forces acting on the car? Okay, which way is the normal force acting?
Perpendicular to the right.
Yeah, so coming out, so I need to somehow indicate that. You know what, why don't we just do a side view of the car? Well, connected with something I said last week, from an overhead point of view, if it's coming out at us, we would do a dot. Normal force there. So if I did a side view, or a back end view, we have a normal force acting that way. So back view, overhead view. All right, what else is acting on the car?
Wait.
Absolutely. Which way is that going?
Down.
In this point of view right here, so that the weight's going that way, and in this point of view, it's going that way. And anything else? Yes, which way is friction acting? You're pointing that way?
In the opposite direction of the velocity or the
Oh,
acceleration.
so that way?
Yeah.
And Rihanna, what were you were gesturing also, I wasn't quite sure which way you were
The
pointing.
same way, opposite way it's going.
Why? Feels right?
Yeah.
Anyone with a differing opinion? All right, anyone go and just stand up and go, how could you even say that?
Well, I feel like if it was going the other, I can't really explain it besides this way, but if the friction wasn't going this way, and going the same way as the car, it really wouldn't have no way for it to stop, so friction helps it either to slow down or to speed up, or something.
Right, but in this particular case, it's going at a constant speed.
Right.
So there is no friction?
Oh, there is friction. Let me
And
read
it
the
is
wording of
going-
the question again, oh, sorry.
So it is going the opposite direction though.
No, it is not. All right. If in the preceding problem, 30 meters per second is the maximum speed without slipping, what is the coefficient of static friction? So there's gotta be friction in there, otherwise, well, I guess I could be asking a question where the answer is 0. But if there were no friction, what would the car do as it goes around the curve?
It was,
Slide because it's not banked.
Which way would it slide?
The outside of the curve. No? Bank. Well, not directly out, but
Is it straight?
yeah.
Yeah, it wants to go straight. It will appear from the car's point of view that it's going to the outside of the curve, but the car's just going straight. What keeps it from going straight?
the centrifugal force,
And what is the centripetal force?
center sinking? I don't know. Is center seeking?
Oh, yeah, okay, it is pointing towards the center of the curve.
Friction.
Yes,
No.
that's the way the friction's acting. Friction's acting that way. Or from this point of view, that way. The static friction keeping it from sliding is acting towards the center of the curve. Anytime anything is going around a curve, there's gonna be some part of the force. There will be some force pointing towards the center of the circle. Some force or some part of a force. And that is gonna be static friction if it's not slipping. And I said if we're at the maximum speed, so what's the formula for maximum static friction?
mv squared or radius?
That would be the centripetal force. Ultimately, we're gonna set it equal to that, but so let's go ahead and put that down. So Fs max, that's my centripetal force. It's gonna be equal to mv squared over r. But the formula, so that is specific to this problem, but in general, what is the formula for the maximum static friction?
I don't know, I don't have it on the top of this formula sheet that you got for us right here.
All right, what's the formula for kinetic friction? That on there?
Those aren't the formulas you put on top for us. We got centripetal acceleration.
Oh,
and
okay, I see what
centripetal
you're saying.
force.
Yeah, the friction formula would show up from chapter 4.
Okay.
Is it M? F Y?
U, not M, U. All right, so the maximum static friction is the coefficient, u sub s, times the normal force, is equal to mv squared over r. That's what we're working with. Now, I don't think, did I give you the mass of the car? I did. Maybe. Yes. So I give you the mass, I tell you the speed, the radius I give you. We just have to figure out the normal force, and then we're down to just one unknown, what we're trying to find. Because that's what we're trying to find right there. So what's the normal force equal to?
Be equal to the mass,
Say that again?
the mass of the car.
The
No,
weight.
but part of that is, it's a force. Force is not gonna be equal to a mass. Despite what's going to be called elsewhere.
The gravitational force.
Yeah, otherwise known as,
Weight.
yes.
Oh.
These two are equal, the normal force and the weight are equal to each other. Well, the weight, what's the formula for weight?
Mg, W equals mg.
Yeah. So, the mass I give you, G, I think we're assuming it takes place on Earth. So we can find the weight, we know the normal force, and then it's just a matter of solving for that. So, doing a little plugging, I'm gonna make up some different numbers than what's in there, or I'm gonna make up numbers that may or may not be the ones that I have in there. So if I say the mass is 1,500 kilograms, G 9.8 meters per second squared. The speed will make 20 meters per second, radius of curvature will make 70 meters. I think that's all that you need. So I gave you radius of curvature, I gave you the mass, gave you the speed. Okay. So on the right-hand side, I know that the total centripetal force has to be equal to mv squared over r, so that would be, given these numbers, 1,500 times 20 squared over 70. That's just a calculator exercise. It would have been convenient if I picked numbers that I could have done more easily in my head. So around 800,000?
I'm sorry, mister, I don't got my calculator and I don't know how to use this phone.
So, you got your calculator broken or just not here?
It's just not here, I was rushing.
It's 8,571.
Oh.
8,571?
0.4, yeah.
Oh, I guess I do know how to work it.
Okay, I see why I was off by a factor of 100. All right, units?
Meters per second? Square? Oh, I'm sorry. What are we looking for?
So this is kilograms here.
Oh.
This is meters per second, and this is meters.
Kilogram.
If you're stopping at radians squared, then no. If you want to just put radians squared in there just for the fun of it, sure. But there's more to it.
Kilograms, meters per second, seconds per second.
Say it again?
Kilograms, meters per second.
Yes.
Oh, I don't like that. That wasn't confident.
Oh, okay. Should have been.
Yeah.
So what we have, in terms of units, the simple way is to think about what did we just find? Or if your brain's not working that way right now, we can go the long way. We have a kilogram times a meter per second. That whole thing is squared over meters. So that's a kilogram times a meter squared over second squared over meters. So we're left with a kilogram meter per second squared. Otherwise known as?
A Newton.
Yes. The centripetal force is equal to mv squared over r, so it's a force, so we better be getting newtons at the end. All right, so that's what the centripetal force equals. I know that the normal force is equal to the weight, which is equal to mg, so that's 1,500 kilograms times 9.8 meters per second squared. Units?
Sorry.
Newtons? Kilogram meters. Sorry, go ahead.
You were saying?
I don't know. I don't know what we're calculating right now, I'm just going through the calculator.
We're finding the weight, and somebody, it was said over here also.
Oh, newtons.
Yeah, it is. Now, you started to say, I think, kilogram meters per second squared, which is
Yeah.
also a correct answer,
Yeah, okay.
but newtons is the easy one. So what I'm saying over here, to plug in these, into what we have over here, I have some coefficient, which is what I'm trying to find, times 14,700 newtons. It's gonna be equal to 8,571.4 newtons. So we have, this is my friction over here, which is my centripetal force, therefore that's equal to NV squared over R. And so we just solve for that. We have to get rid of this, so we divide. So it goes 8,571.4 divided by 14,700. Which is 0.64. Somebody's gonna tell me what the real answer is.
1.715.
0.715?
715, yeah. Or 1.715.
No, it can't be more than one. There's the decimal point right here at the 4, I don't know if you missed that or spec,
I got 0.58. Oh,
Yeah,
wait, no.
0.58.
0.58.
Yeah, 0.58.
My numerator is smaller than my denominator, so it can't be bigger than 1.